Hello everyone, I am Saeed Al-Abri, a postdoc at the Georgia Tech System Research Lab. Today I will talk about a derivative-free distributed optimization algorithm with applications in multi-agent target tracking. This work is in collaboration with my colleagues Tony Lin, Robert Nilsson, and my supervisor, Professor Fumin Zhang. We consider a swarm of agents where at each instant of time, each agent is able to capture an image about a target moving with unknown dynamics. The problem is then to design a distributed control law so that the swarm detects and tracks the target. A challenge we consider here is that the agents have limited communication resources and thus cannot communicate images. Our solution consists of two main steps. The first step is to design a mapping function that transforms the high-dimensional image information into a low-dimensional scalar cost function. The second step is to design a control law to optimize the perception-based cost function. In our design of the perception-based mapping function, we consider an object detection function G that is able to draw a box around the target in the image frame. From the points of the box, B1 and B2, for example, we design a cost function that is optimal when the target is completely contained in the box. Here we leverage the existing AI-based perception algorithms for the object detection. Once we design the cost function, the planning and control laws are designed to optimize the collective cost function of the entire swarm. We leverage our previous derivative-free SUSD optimization algorithm to solve this distributed optimization problem without requiring analytical forms of the perception-based cost function and without requiring communication of images or cost values. Here we use a distance-based cost function Z for a simulation in 3D environment on the left and for a 2D Robotorium implementation on the right. Note that here we only require the distance to the target, which is much cheaper to implement practically than requiring the relative positions. Here we use the image-based tracking function Z of G that we have presented in the previous slide. And as you can see here, all what we need to do is just to change the cost function. Results. The first one is about the formation control. The second result is about the optimization. And the last one is about the tracking performance. Please stop by our poster if you have any questions. Thank you for listening.
Hello, everyone. Welcome. Today, my presentation topic is the Lyapunov theory for finite sample guarantees of asynchronous Q-learning and TD learning variants in reinforcement learning. This is a joint work with my advisor, Professor Maguluri from Georgia Tech, and my collaborators, Professor Shakotai from UT Austin, and Dr. Shamagun from IBM Research, New York. We first consider solving a fixed point equation using stochastic approximation algorithm. So here, the target fixed point equation is f bar of x equal to x. And the stochastic approximation algorithm for solving it is presented here. The sequence yk is a Markov chain with stationary distribution mu. And the operator f bar of x is a contraction mapping. It turns out that most of the popular reinforcement learning algorithms, such as Q-learning and variants of TD learning algorithms, can be modeled this way. We next present our main results. For simplicity, we consider using constant step size alpha here. So for properly chosen constant step size, we have the following finite sample bound. As we see, the right-hand side is composed by two terms. The first term converges to 0 geometrically fast as the number of iterations tends to infinity, while the second term is a constant, which is roughly proportional to the step size we use. Geometrically, this means that the iterates xk converges exponentially fast to a ball centered at the target solution x star, and the size of the ball is roughly proportional to the step size. Our proof idea is based on a novel construction of Lyapunov function. Please see our paper for more details. Using this unified results, we have the following sample complexity bound for the popular Q-learning algorithm. This bound is the state-of-art mean square bound. in terms of the accuracy, the dependence on the discount factor gamma, and the dependence on the size of the state action space SA. Similarly, we can derive sample complexity result for the n-step TD learning algorithm for solving the policy evaluation problem in reinforcement learning. Specifically, we see that our sample complexity bound is an explicit function of the parameter n. So we can optimize this sample complexity to get the optimal choice of n, which is the following. And this is the first known result. We also derive sample complexity for the popular TD lambda algorithm and off-policy V-trace algorithm. Please see our paper for more details. Thank you for listening.
Hello everyone, my name is Akib Syed and I will be presenting on the experimental design, control, and learning of Moreflix, a smart morphing wing system. This is joint work with my advisor, Dr. Kyriakos Vamoudakis. Consider a typical section of a NACA 44-18 airfoil which has chord length C and is subject to a lift force L acting at the quarter chord and a corresponding pitching moment. The quarter chord is also known as the aerodynamic center. In essence, we seek to prevent rotation about the center of gravity of the airfoil in order to stabilize it. To this end, we denote point G as the center of gravity of the system and some moments over this point. We normalize the moment about the center of gravity and require the moment about the aerodynamic center to be equal to 0 for stability, which results in the expression for the moment about the aerodynamic center of the morphed airfoil. Morphing the airfoil alters the camber, thereby reducing the curvature at the trailing edge. The modified airfoil is called a reflexed airfoil. Introducing reflex to the airfoil in essence reduces the camber in the trailing edge region while also causing a change in the pressure over the system, thus reducing the lift over the trailing edge and subsequently generating lower magnitudes of nose-down pitching moment. We call our prototype Moreflix. This is a portmanteau of the words morph and reflex. Now, in morphing the system, we stabilize Moreflix as the pitching moment coefficient for the morphed configurations at the same angles of attack attain more positive values than their cambered nominal counterparts. We implement a Markov decision process framework to model the effects of the servo actuation in order to induce morphing on the aerodynamics. Here we have that S is the set of state spaces and A the set of actions, which are both in Rn. Additionally, we define T as the transition function, which specifies the probability of transitioning to the updated state when an action is taken at the initial state. In the present framework, the probability of taking this next step is assumed to be 1. R is the reward function, which is commensurate with the transition and designed such that the ideal behavior is encouraged. We leverage a Q-learning framework in order to determine the optimal value of the pitching moment coefficient for the morph states of Moreflix. The algorithm leverages an epsilon greedy policy, and the Q function is obtained using dynamic programming and expressed using a Bellman equation, which simplifies calculating the Q function. The Q function in this case is simply a sum of the immediate reward and discounted future values. Designing the airfoil was an iterative procedure, which first entailed fabricating a CAD model using SolidWorks and then 3D printing the parts for this model. The 3D printed prototype is comprised of a rigid leading and trailing edge, servo motors, truss elements, pull levers, and a compliant upper morphing skin. The procedure for fabricating the final 3D printed prototype of Moreflix was to first design the parts using a CAD software, and then 3D print the parts, and then finally form them into the final prototype. The control of Moreflix is facilitated using two Emacs ES09MD digital servos. The control is enabled using an Arduino microcontroller. Now, controlling these servos is a constrained optimization problem with the constraints arising from the structural limitations which come from the electromechanical components of the system. Morphing is primarily an electromechanical process here. Now, the electrical input generated to the system using the Arduino servo input initiates the motion of the pull levers, which exert tensile and compressive loadings on the guitar strings. The strings move in opposing directions to one another and induce a motion of the truss elements, which impart loading to the morphing skin. This, in turn, results in morphing of the system itself. The experimental methodology was comprised of two portions. The first of these was obtaining the photos using a real-time morphing photo acquisition setup. The next process was to convert the images obtained using this photo acquisition and converting them to airfoil coordinates. Now, for the real-time morphing photo acquisition, we used a camera which had to have been synchronized with the morphing motion of Moreflix. This, in turn, entails obtaining real-time images of the system as it goes through the user-specified servo angles. Following this, we leveraged an edge detection algorithm to effectively convert the photos into airfoil coordinates, which were then imported into a CFD solver. Then, the optimal aerodynamic value was obtained using the aforementioned learning algorithm. We provide results from the simulations which are obtained using the experimental results. In the top left graph, we have a graphical representation of the total rewards versus the episodes. We find that as Q-learning progresses through the training episodes, the total rewards per episode increase. Then on the top right graph, we have the percent difference between the goal pitching moment coefficient and this current state pitching moment coefficient. This graph gives a percent difference between our desired state and actual state at each iteration. The table in the center provides some example cases. The bottom graph depicts the visualized path trajectories to the goal state based on Q-learning. Successful searches necessitate significantly more iterations compared to Q-learning. That's about it. Thank you for your time, and please feel free to contact me at my email address if you have any questions whatsoever. Have a great day.
Hi everyone. So today I will be talking to you about my research. So the movement of a particular species of fish can be given by the persistent turning water model, and this model can be characterized by a constant swimming speed and a minimal change in the headings at two consecutive instances of time. Here the angular velocity is shown by omega, and the model inherently incorporates a wall avoidance term and does not require any localization service such as a GPS. An interesting observation in the PW model is the role of the value of sigma. So here sigma basically defines the stochasticity in the movement. As the value of sigma increases, the movement looks more like a random walk, and vice versa for smaller values of sigma. The inclusion of the sigma term enables the model to show a wide variety of different behaviors because the model becomes stochastic. And even though the PW model incorporates obstacle avoidance and is localization free, but it is a non-linear dynamical system, and it can be non-trivial to evaluate its global properties using conventional methods. So in order to evaluate the behavior of a fish which moves according to this model, we use Markov chain theory. So we use a really powerful method introduced in the 1980s, which can be used to analyze the dynamical properties of a non-linear dynamical system. This method is termed as a generalized cell mapping method, and it can be used to convert a non-linear dynamical system into its state transition matrix. So the first step involves discretizing the continuous time version of the PDW model, and this is followed by identifying the states which can be used in order to formulate the transition matrix. The two main challenges in using GCM method is a proper discretization of the model and the identification of the states. In the PDW model, we have actually used a set of 8 states of discretized headings, and in order to formulate the transition matrix. We also discovered that under a range of values of sigma, the given structure of the Markov chain, the given structure of the PDW model satisfies the structure which is given here on the right. So compared to other random walk strategies, we can observe that the PDW model, it exhibits no backtracking. In other words, the PDW model, in the PDW model, the agent does not move backwards. In order to ensure coverage, the probabilities of the transition matrix in the red region need to be greater than 0. And we can prove the coverage of a model having the given transition matrix by using reachability analysis in the Markov chain theory. In short, we can actually show that the diagram of the Markov chain of the headings are strongly connected, and the diagram of the headings can then be translated to a diagram of a small search space motif, which can be used to make the entire search space. And we have proved in our previous works that the diagrams of adjacent search space motifs overlap with one another, and hence there's always a path to go from one point to another in the search space. In other words, the diagram of the entire search space is strongly connected, and hence the PTW model can be used as a coverage strategy. And this slide basically just shows a comparison between different random walk strategies, which are similar to the PTW model. And we can see here that the PTW model is seen to cover the area at a much greater rate than the other two strategies. Hence, PTW model can be used as an effective coverage strategy in GPS-denied environments. Thank you so much.
Hello, my name is Christopher Banks, and today I will be presenting to you LTL motion planning of multi-robot systems using cross-entropy optimization. This work seeks to answer the problem of delegating tasks effectively to a team of robots, where such scenarios where this can occur are search and rescue, precision agriculture, and surveillance. More formally, how do we determine optimal individual assignments for a multi-agent team of quadcopters given a high-level user specification? We do this by representing our robots as graphs. Each robot is represented as the following tuple, where we can easily represent both states and actions available to an agent. By constructing what's known as an agent transition system, by doing the product of the environment and robot, we're able to create the agent transition system. This allows us to define actions available to a robot based on its internal state and location. In addition to this, using LTL, we can specify desired temporal properties for systems which we define as transition systems. LTL specifications can be formulated as non-deterministic finite automaton, or NFAs, such that a satisfying trace which goes through this non-deterministic finite automaton satisfies the LTL specification. By generating the product between the NFA and agent transition system, we're able to generate the planning automaton. A team automaton can then be developed as the union of n agents planning automaton. Prior work has shown that LTL specifications can be decomposed over finite traces for multi-agent systems using a specific subclass of LTL formulas, such as cosafe LTL specifications or finite LTL specifications. We propose the multi-agent task allocation via cross-entropy algorithm, such that given a team automaton and the cost functions associated for each agent, we can delegate trajectories to all agents. We do this by iterating through the team automaton offline and then find trajectories such that we minimize the cost associated with an agent performing a particular task. Then we assign that agent the trajectory to complete that task. Following this, we assign trajectories to each quadcopter. We optimize our tasks using the cross-entropy optimization method, which is the following. So we sample trajectories from some distribution. Then we pick the best subset according to a desired cost. Following this, we repeat this for a specified number of iterations, and then assign trajectory sequences that minimize the total cost for a single agent. We use the following case study to validate our algorithm, where we consider a set of quadcopters and two goal locations, one of which is on fire. The agents must then decide, based on our LTL specification, which agents are to collect water and perform and go to put out the fire for, say, location B, and to observe location A. We represent our global goal as eventually visiting location 1 and location 2, and to ensure that you're carrying water if you visit the smoke location. Our agent cost function is the sum of the total distance of a trajectory plus the input cost, followed by our state propositions, which we define as ellipsoids. Our results show that for the three quadcopters, quadcopter 0 visits water in location 2. Quadcopter 1 only visits smoke, and quadcopter 2 visits water in location 1. In conclusion, we have shown how to go from high-level specifications to multi-agent actions. We've presented a sampling-based method of task allocation, and we show that for agent-specific cost functions, we can develop a selection optimized framework. Thank you.
Hi, my name is Tony Lin. I'll be talking about our ongoing work titled Miniature Blimps for Server Farm Temperature Monitoring today. So the primary focus of this work is to provide overheating server farms with an additional form of monitoring systems. A lot of these kinds of overheating server farms can overheat and shut down without these kinds of systems. And this can cause either a loss of service, which is a large economic value, or possibly a loss of valuable data, which is a valuable product. And so lots of these kinds of servers can have their own internal temperature sensors, but this can result in a huge amount of data to process. And then also some of these servers have been shown to be spoofed previously. And these kinds of sensors can be leveraged maliciously. So adding an additional layer of monitoring is still valuable, at least to help deal with these kinds of malicious cyber attacks. So our proposed solution to this is to do this kind of monitoring using an autonomous robot blimp. And so in this work, we'll use the Georgia Tech miniature autonomous blimp to try and do this autonomous temperature monitoring. So one of the main difficulties in this work is that we're trying to address is how do we perform autonomous flight when we're being affected by high winds. So in these high compute server environments, a large amount of cold air is pushed through these server racks to draw out the hot hot air from the servers. And so while the blimp is flying through this environment, it has to deal with being affected by these high winds. And so some of our ongoing work about controlling the blimp is related to actually doing disturbance rejection for the blimp so as to avoid having large roll and pitch oscillations. So shown in the bottom right is an inner loop, outer loop controller that we use to do velocity tracking for the Georgia Tech miniature autonomous blimp, which relies on a roll and pitch angle feedback from some external source. So in the video shown on the left, as my collaborator tries to disturb the blimp with a small pull on its tail, you can see that the blimp is able to rewrite itself and maintain a very steady flight, continuing forward at 0.2 meters per second. So some of the work we've been doing has been to provide the blimp with an onboard sensing option instead of using a motion capture system to provide this state feedback. And so what we've done is we've been able to add a mounted IMU and camera to provide this kind of roll and pitch angle estimation for the blimp. And so in our initial test using this combined onboard sensing for the GT map with disturbance reduction, in Dr. Joshi's server farm lab, we were able to try and see how well the blimp was able to do this kind of disturbance rejection using our controller and this onboard feedback. And so some of the performance of our IMU is shown here on the screen as well. And you can see that it's not perfect, but it still does reasonably well. But despite this, even with this IMU feedback, we were able to do some damping of the oscillations and roll and pitch. But for now, we were just doing manual control for velocity. And you can see that at least for my piloting skills for this manual control, I'm not able to maintain desired control within this region. So this suggests that actually what we need to do is something more advanced, something related to actually mapping and understanding what the forces of the winds and what directions they're going in, at least in the XY planar positions, to be able to maintain tracking behavior in this desired orange region. So some of our previous work in our group is related to actually doing online field estimation, but specifically for oceanic environments. So we can try and apply this work actually for our wind field identification problem. So the method uses some ideas from adaptive control and uses the error between the actual measurements of our true position and then a predicted trajectory based on our estimates of certain parameters of the wind field. And so by combining these two elements together and using a parameter update equation as a dynamical equation, we're actually able to get very good estimates of the wind field, just at least in the simulation you can see, as you can see. So in this simulation, the red dot is the true blimp's position. The yellow dot would be the predicted blimp's position based on our current estimate of the wind field parameters. And the blue arrows and the red arrows show the spatial variance of the wind field. And as you can see over time and over various turns and trajectories through this environment, the blue arrows steadily align themselves with the red arrows here. So our proposed approach to trying to solve our server farm temperature monitoring problem, at least at a certain single point, is to use the combined wind field estimator with a controller input to try and reject the kind of wind vector we expect to see at a certain location, and using the developed camera and IMU sensing we developed in this past semester to provide the observation feedbacks necessary for performing both the wind field estimation and the controller input. Thanks for your time.
Hello, my name is Shravan Ravigopal, and I'm a first-year robotics student advised on this project by Professor Brooks Lindsay and Professor Jaydev Desai. I've been focusing on a preliminary study on the progress towards real-time tracking of medical guide wires in 2D and 3D ultrasound. This will be an important step in generating automated medical robots that can help physicians perform surgery more efficiently and more accurately. But first, why is this important? We need to track the accurate pose of medical devices inside the body during interventional procedures. Many interventional procedures use X-ray and fluoroscopy methods to localize the medical robots. However, those have the drawback of having high radiation exposure for both the patient and the physician, and ultrasound can decrease this radiation exposure. Then, with the 3D localization, we can provide a method to automate the movement of the medical robots through time, saving time on the surgery. Also, accurate localization of the guide wire and its surroundings can be used for surgical path planning for physicians. Current strategies to work with ultrasound in ultrasound tracking are visual servoing methods to stabilize a moving area of soft tissue for tracking, and also multiple model data association methods, which can determine the change in the shape of the walls of the chambers of the heart through time. Our project is done by first having a 2D tracking of a robot through synthetic data sets. Then we'll use a real-time tracking of a moving robot using a data set that we acquire using our ultrasound. Then we will obtain a 3D volume using the ultrasound, using a phantom vasculature, and then find the 2D slices, which can be generalized to fit inside the 3D volume. First, the setup of this uses a phantom vasculature with a trifurcation with the guide wire inside. Then we use the water tub as an imaging medium so that this phantom vasculature is visible during ultrasound. Then we use for the 3D volume acquisition, we use the Mitsubishi PA10 robot inside the water tub, and we use a GE9L linear array transducer to traverse horizontally through this phantom vasculature at a velocity of 1 centimeter per second in order to obtain all of the 2D slices that is required to get a 3D volume of this entire phantom vasculature. For two-dimensional tracking, first we use the synthetic data set. We use EchoNet dataset, which is a data set of beating hearts in ultrasound. Then we superimpose an image of a medical guide wire that moves through this ultrasound video, and we use a constant velocity Kalman filter tracking method to track this medical guide wire through time. Then for the 2D semantic segmentation tracking, we use a modified ResNet 50 architecture to find the location of the guide wire through the phantom vasculature that we have in our lab. And we trained this ResNet 50 deep learning architecture through pre-labeled data sets, which we create by first obtaining a video of the guide wire traveling through this vasculature in ultrasound, then labeling each frame as either part of the guide wire, the path that the guide wire can take, or the background of the image. This semantic segmentation takes less than a second and an average of 0.23 seconds to compute. Thus, it can be used as real-time tracking for medical applications. Then, for three-dimensional localization from the 2D tracking, first we obtain the 3D volume by the linear motion of the transducer using the robot arm. Then we use the 3D volume to find each of the 2D slices that can be used to find the guide wire through time. Slice 1 shows a horizontal cross-section of the 3D volume with the trifurcation vasculature clearly visible. And slice 2 is a diagonal slice of this 3D volume, which also has the trifurcation vasculature visible. And the 2D ultrasound data can be used by registering each 2D slice as part of the 3D volume. And this can be done using slice to volume medical image registration methods. And many methods are there, such as fast feature detection, iterative closest point approach, and HAR basis filter feature matching. This is planned as future work for this semester. Thank you for your time.
Hi, I'm Allison Jenkins, and my project is developing a motion intent machine learner for an upper limb prosthesis. This project is sponsored by the NSF ARMS program and advised by Dr. Sawicki and Dr. Young in the Woodruff School of Engineering Mechanical Engineering Department. The goal of the wearable robotics project is to design a motion intent machine learner for an upper limb prosthesis adaptive controller that's both robust and practical for clinical trials and daily use. The Luke arm, as you can see in the figure, is the upper limb prosthesis to be controlled based on a user's motion intent. This upper limb prosthesis with an adaptive gain controller for motor joints is based on a high-level force control and a low-level position or velocity control. 2 IMUs and 2 sets of EMG sensors are placed on the user's upper arm, and they are used to capture the kinematic motion data and muscle activation data respectively. Each set of data captured for a specific user is used to calibrate the existing motion intent correlation framework, which was created using a pre-trained general database. And this is done by the machine learner. You can see it's just a simple neural network. And the TSK fuzzy logic system takes in the general motion states, feeds them through a triangular decision function, and outputs the motion intent classification. The motion intent machine learning outputs are then sent to the prosthesis controller, which adapts the control gains accordingly. Thanks for listening to my project talk, and I'd be happy to answer any questions. Thank you.
In this work, we investigated differentiable optimization in robust learning tasks. The project is under supervision by Dr. Patricio Villa and Dr. Yongxin Chen. Our problem can be formulated as a bilevel optimization problem where the variable x in the auto-optimization is subject to the optimality in the optimization problem. Our task is to find a good parameter set so that the objective function in the auto level is minimized. We face 2 challenges. First, the constraints are unfriendly for neural network training, such as SJD or ADAM. The second one is we have a very special constraint. How can we differential argmin? We present the first general way to solve the bilevel problem, named the enrolling algorithm. It iteratively optimizes the x for fixed step, approximate x star by xk. In this way, we can evaluate the objective function. The involution of x forms a computation graph. With the forward computation graph, we can run backpropagation to acquire the gradient information, and the derivative of x star is approximated by the derivative of xk. In a summary, with the enrolling algorithm, we relax the argmin constraint by using a suboptimal xk. The approach only requires the existence of the computation graph x. Meanwhile, the size of the computation graph grows linearly with the number of steps k. If we want a good approximation, the algorithm has a high computation and memory constraint. The second approach, named the KKT-based, if we look closely at the inner problem, while the inner problem is a standard convex problem, the optimality could be described by the KKT equation. If we differentiate through KKT and with some math manipulation, we can acquire the closed form of derivative of x star, and the derivative only depends on the parameter of objective functions and constraint, independent of how we solve x star. Here is the takeaway of a conclusion. We have a closed form of derivative, and we almost get the gradient for derivative for free, since the Jacobian and Hessian is calculated during the forward process. And but it requires the problem. The inner problem is a convex problem. We verify our algorithms on the Starker-Burger game. The simple problem has a closed form solution. We can verify the correctness of 2 algorithms. We profile the time consumption of 2 algorithms. We could see that the KKT-based algorithm almost twice as fast as the enrolling algorithm. Next, we consider the auto-tuning controller for path tracking with a bicycle model. Given a reference path, our auto problem is trying to minimize the lateral path deviation with minimum control energy. Well, the inner problem is we present our controller by minimizing the estimated cost function. Our goal is trying to find a good cost function such that the vehicle can stay in a reference path. The learning process is online, so after several iterations, we can see with the tuned policy, the vehicle checked the path well. Thank you.